So, hello everyone. Welcome to the week 4 session. My name is Abhishek Pandey. I am a primary at IT Bhubaneswar, and today we are going to discuss about week 4 assignment. So, the questions will be based upon these contents: closed sets, closure interior of a set, a neighborhood and limit points, Hausdorff space and convergence of a sequence, and continuous function. Okay, so I think the screen is visible. Is it? Okay, so let X be a topological space and A be a subset of X, then A is said to be closed if X minus A is open, means X minus A belongs to the topology. Okay. Okay, so for the closed set, we have the following properties, that phi and X are always closed. Just wait a minute. And arbitrary intersection of closed sets are closed. Finite union of closed sets are closed. Okay. The second thing is, let Y be a subspace of X, then a set A is closed in Y if and only if A can be written as B intersection Y, where B is a closed set of X. Okay. So just I am recalling the basic facts before solving the problem. Closure interior of a set. So given a set A of a topological space X, interior of A is nothing but the union of all open sets contained in A. Okay, and closure of A is nothing but the intersection of all closed sets containing A, means it is the smallest closed set containing A. Basically this result is well known, that interior of A is contained in A and A is contained in A closure. If A is open, then interior of A is A, and if A is closed, then A closure is A. We define the neighborhood in a topological space as U is said to be neighborhood of a point X belonging to a topological space capital X. Let me just write it down here. If U is an open set containing X. Okay. Now, what do you mean by limit point or cluster point or accumulation point? So, if A is a subset of X, topological space X, and if you take any point X belongs to X, we say that X is a limit point of A if every neighborhood of X, means any open set containing X, the intersection of that open set with A minus the singleton X should always be not equals to phi. So, this is the definition of limit points. So, we have basically results. Basically, the A closure is nothing but A union the space of all limit point, means the set of all limit point, which is denoted by A dash. So, A closure is equals to A union A dash. Okay, so a subset of a topological space X is closed if and only if it contains all its limit points. Okay. Now, okay, so here we have a topological space X, and suppose we have a subspace Y. Okay. Consider a subset A of Y. Okay. Then the closure of that subset A in Y, in general, it is different from closure of A in X. For example, you can take let X is equals to R and Y equals to open 0 close 1 and A equals to open 0 and open 1 by 2. Then the closure of A in X is close 0 comma 1 by 2, and closure of A in Y is open 0 comma close 1 by 2. Okay. Is it clear? Okay, so if you have any doubt, just let me know. You can. Okay. So this is the result when we can say that a subset of Y, the closure of A in Y, how to represent the closure of A in Y in terms of closure of A in X. So basically the closure of A in Y is nothing but the closure of A in X intersection Y. Okay, the proof is there in the lecture notes also. Okay, so we will move towards our problem 1. Okay, so let X be a topological space and Y be a subspace of X, then which of the following is / are true? First one is let A be a subset of I, then closure of A in X equals to closure of A in Y. So the first thing is obviously it is not true. So first one is false. Basically you can see the remark 1. Okay, so basically closure of A in X not necessarily equals to the closure of A in Y. This is the example, remark 1. Okay, see remark 1. Okay, second statement is again true. So this first is true, second, sorry, first is false, second statement is true, this mentioned in the result 3, that closure of A in Y is nothing but the closure of A in X intersection Y. So second is true, result 3 I guess. Yeah. Now let A be a subset of Y. If A is closed in Y, then A is closed in X. Okay, so this is not true obviously. Basically we will solve the fourth one. If A is closed in Y and Y is closed in X, then A is closed in X. Okay, we will solve this one. So fourth one is okay. So suppose A is closed in Y. That is Y minus A is open in Y. Okay, so that is there is some U open in X such that U intersection Y is nothing but Y minus A. Is it clear? I hope it is clear. Okay, so therefore X minus U is basically closed in X, isn't it? Okay. Consequently, since A is subset of Y, we have Y intersection X minus U is basically Y intersection X minus Y intersection U. Okay, which is nothing but Y minus A, and which is nothing but A, isn't it? So basically A is nothing but, we have written A in terms of X minus U intersection Y. Okay, so means it means that, so see, this is a closed set in wait a minute, so Okay, yeah. So this is closed in X, closed in X, and by hypothesis, uh, by hypothesis, Y is closed in X, so their intersection is also closed in X. So A is closed in X. Is it clear? I hope this is clear. So fourth one is true and third one is false. Let us look at the fifth one. If it is not clear, please let me know. Fifth one is asking if U is open in X and A is closed in X, okay, then U minus A is open in X and A minus U is closed in X. So let U be open in X and A is closed in X. Closed in X. Okay. So since A is closed in X, means X minus A, this is open in X. Okay. So we have basically U intersection X minus A is nothing but U intersection X minus U intersection A, which is nothing but U intersection X is again going to be U minus U intersection A, okay, again which is nothing but U intersection, sorry, U minus U, and so this will be union U minus A, okay. Now this is nothing but U minus A, so we got that U intersection X minus A, so U intersection X minus A is nothing but U minus A, okay. So U is open, this is open, and since A is closed in X, by definition this is open, so intersection this is open in X, okay. So U minus A is open X. So now the second thing is this set X minus U is closed in X, okay. So because U is open in X, means X minus U is closed in X, so we have A intersection X minus U is basically A intersection X minus A intersection U, which is nothing but A minus A intersection U, which is nothing but A minus A union A minus U, okay, which is nothing but A minus U, okay. So now what was the thing? This was closed in X by hypothesis, and since U is open in X, so X minus U is closed in X. Now this is equal, so now A is closed in X and this is closed in X, so their intersection is closed in X. But what is their intersection? Intersection is A minus U, so means it is closed in X. Okay, so this is true. Fifth one is true. So I hope it is clear. Please let me know if it is not clear. This is fine? Okay, so we will move towards our next problem. Problem 2 is, so consider the following topologies on R. First one is standard topology, second one is finite complement topology, lower limit topology, K topology, upper limit topology, and discrete topology. We need to determine the closure of the set 1 by n such that n belongs to Z plus, means natural numbers. Okay, so we will do this one. Okay, so let us look at the solution. Okay, so just note that closure of a set A is nothing but A union A dash, where A dash is the set of all limit points. A. So we need to find the set of limit points of A, where A is nothing but 1 by n such that n belongs to Z plus. Okay. Okay. So we will first do with the standard topology. So clearly 0 just noted by A. So clearly 0 doesn't belongs to A. Okay. Any neighborhood of 0, any neighborhood of 0 contains an interval A comma B, where A is less than 0 and B is positive. Okay. Now if n belongs to n, where n is greater than 1 by B. Okay. So B is nothing but the neighborhood, what you are getting, AB. Okay. Means, it's fine. So if n belongs to n, where n is greater than 1 by B, then basically 1 by n is less than B. Okay. And is contained in U. Okay. So therefore 0 is a limit point of A. Okay. Is it clear? So we only need to see that this A comma B should intersect with A. Okay. This is the only thing we need to see here. Is it fine? So if you take, just wait a minute. Am I audible? Mohana Krishna, am I audible? Okay, thank you. Okay, so any neighborhood of 0 contains an interval a comma b where a is less than 0 and b is greater than 0. Okay, so now any n you take any n which is greater than 1 by b. Okay, because you can always find some n which is greater than 1 by b. So 1 by n will always be less than b. So all these things will be contained in u. So therefore u is a 0 is a limit point of a. No other than 0 there is no limit point. No other point in R is a limit point of a. Okay, because if if c is less than 0 or c is greater than 0, okay, wait a minute, if c is less than 0 or c is greater than 1, means c is any point which we are considering as a limit point. So suppose c is less than 0 or c is greater than 1, then basically minus infinity comma 0, okay, and 1 comma infinity, basically this do not intersect. So these are the neighborhood of c and 1 which does not intersect with the set k a. Okay, so means these points cannot be limit point. Again, if c belongs to 0 and 1, okay, so let us consider the first case. If c is equals to 1, then you can always find, I mean, like then you take any point 3, 4 to infinity. So this is a neighborhood of 1. Okay, basically this is starting from a is nothing but 1, 1 by 2, 1 by 3, 1 by 4. Okay, so you take any 2 points in between this one, 1 and 1 by 2. Okay, and you just take the neighborhood going to infinity. Okay, like this one, 3 by 4 comma infinity. Now 3 by 4 is greater than 1 by 2, okay, but less than 1. Okay, so 3 by 4 comma infinity is a neighborhood of 1 but does not intersect. Does not intersect. Okay, so 1 is also not a limit point. Okay, does not intersect a minus 1 because 1 we have to remove. Now suppose c is 1 by n itself, c is of this form, okay, for some n greater than 1. Okay, so in this case what do we need to do? Then if you take 1 by n plus, wait a minute, okay, so 1 by n, so you take this one, 1 by n plus 1 comma 1 by n minus 1. Is it the case? Oh, sorry. Wait a minute. Yeah, so this is the thing. So this contains C, but does not intersect A minus C. Okay. Now the only thing is, if C is not of the form 1 by n for any n. Okay. Then by, so up to this everything is clear. Then by the density of rational numbers, so there are alpha comma beta belonging to Q, okay, such that alpha sorry alpha comma beta belongs to Q, where now we have this one, 1 upon n plus 1 is less than alpha is less than C is less than beta is less than 1 upon n for the appropriate n. Okay. So now if you take alpha beta, okay, now take the neighborhood alpha beta, take alpha beta as a neighborhood. Now again, alpha beta does not intersect A minus C. Okay. So again, so 0 is the, so 0 is the only limit point. Okay. Now this is the with the standard topology, first one. Now we'll see the finite complement topology. Finite complement topology. So means, I think it is R with T2. So in this topology, we need to find the closure of this set A. Okay. So in the finite complement topology, given C belongs to R, any neighborhood of U of C must contain 0 comma B for some B greater than 0, isn't it? So what is the so any neighborhood of C means open set which contains C. What are the open sets in this finite complement topology? Open sets in finite complement topology means all those sets whose complement is finite. Okay. So now if it contains C, then it has to be contained like it has to contain 0 comma B for some B greater than 0, isn't it? Mohan, is it clear? So basically u is open means r minus finite complement, so u is finite. Okay, so suppose if if u does not contain contain 0 comma b for some b positive, then what would happen? It means that, so u does not contain 0 comma b. It means that x minus u basically contains, so x minus u basically contain 0 comma b, which is nothing but which is infinite, so this is the problem, so it has to contain this thing. Okay, so this just for explanation. Okay, so accordingly 1 by n belongs to 0 comma b. Okay, and which is contained in u for all n greater than equals to 1 by b. So every real number is a limit point of A. So A closure is nothing but A union R, so which is nothing but R. So A closure is R in the okay. So basically this also says that which we will see later once we are talking about Hausdorff. It says that in the finite complement topology, every so this sequence, this says that, this we will see later, sequence 1 by n converges to every point of R. This we will see later. Okay. So this is basically finite complement, just remember. Now the third one, okay, so third one is K topology. So let us see the R with K topology. Okay, so for the same reason, like, so this basically contains the intervals a comma b and a comma b minus 1 by sets of the form 1 by n. Okay, so for the same reason, no c less than 0 or c between 0 comma infinity can be a limit point of A. Okay, again any neighborhood of 0 cannot include 1 by n for any n belonging to n. So why such thing? Any idea? Is it clear to you, Mohana? So this comes from the topology itself. So, so since A does not have any limit points, so A closer, okay, which much? So where is the problem? In this one? Okay, so this is basically from the, just wait a minute. Wait. So this part notes no C less than 0 or C greater than 0 can be a limit point of A. That can be done in the same way the we have done for this one uh, in the standard topology. Okay. The problem with the any neighborhood of sorry, I should not write like this. I should write like so. Basically, you can find neighborhood. So there exists neighborhood of 0, which 0. So which does not include, which does not means. So these are the neighborhoods of the form basically A comma B minus this set K, which is of the form 1 by n. So in this neighborhood you are already excluding this 1 by n. So how they are going to intersect this set 1 by n? So means 0 is not a limit point of 0 is not a limit point of R with the finite complement topology. Is it clear? Sorry, 0 is not a limit point of A when you are giving R as a finite complement topology. Is it clear now? So in this case, A closer is A. Now is it clear? Because see, we need to find a neighborhood which does not intersect. The condition for the limit point is every neighborhood should intersect, removing that point. So we need to find a neighborhood which does not intersect. So obviously in the K topology, you have neighborhoods of the form A comma B minus 1 by n. So this is done. 0 cannot be a limit point. Is it clear? Okay. Now the next thing is upper limit topology. So R with T5, I guess. T5. So in this one, for C less than equals to 0 or C greater than 1, okay, the neighborhoods, sorry, the so the neighborhoods infinity C and 1 comma C, okay. So in the upper limit topology, these are the open sets. Means open sets formed by the basis A comma B. and in the lower limit topology a comma b is there. Okay, so upper limit topology you can do with the lower limit topology. I will not explain the lower limit topology part. I will just explain the upper limit topology part. So the neighborhoods minus infinity to c and 1 to c basically just wait a minute, c do not intersect a. Okay, that is quite clear. Now if c belongs to 0 1, okay, there is some n belonging to natural number such that 1 by n plus 1 is less than c is less than equals to 1 by n. Okay, and the interval becomes 1 by n plus 1 comma 1 by n, so is a neighborhood of c. Again 1 by n plus 1 comma 1 by n intersection with a, and we have to remove this 1 by n, okay, is again 5. So this cannot be, so this is a neighborhood which does not intersect with a other than 1 by n. So these points are also not the limit point. So a does not have any limit point. A does not have any limit point. Okay, so a closer is nothing but a in this topology. Now the last one is a discrete topology. Okay, so okay, so R with discrete topology. Okay, so in this case we know that in discrete topology every set is open set. Okay, so means every set is a closed set also. So a is 1 by n, which is 1 by n, okay, such that n belongs to z plus. So a is closed, okay, in the discrete topology, and for a closed set the closure of a is nothing but a. Okay, so so this is the closure of a. Okay, what would be the limit point? I mean any point, so it doesn't have basically I can say that, so limit point if you take a dash, which is this is nothing but 5 for a in this case, because again this if you take any point of this c belongs to R, then singleton c is a neighborhood containing c. Okay, now if c doesn't belongs to a, this is not going to intersect. If c belongs to a, so c intersection a minus again c, this is 5. Okay, so it doesn't intersect. So in the discrete topology again it does not have any limit point. So basically its closure is a. In fact, it is closed. Okay, so even a closed set, so this closed set, okay, in the set of, so this, remember that a closed set can have no limit point. Okay, this closed set does not have any limit point in the in the discrete topology. Okay, Basically, its limit point set is 5. Again, it is contained in A. Closed set will always contains all its limit point, but it is not guaranteed that every closed set must have a limit point. Okay. Is it clear, Mohana? So I think we have done all this one. Okay, let us move to the next problem. Okay, so this is the problem 3. Consider the following topologies on R. Just wait a minute. Okay, so yeah, solution. So consider the following two topologies on R: lower limit topology and topology given by the basis, this one. Remember that the uh, topology generated by this basis is different from the standard topology. Okay, like means if you take this basis a comma b such that a is less than b and a comma b belongs to q, this generates the standard topology on R if you consider this as a basis. But if you consider this as a basis, this generates a different topology. Okay. So let us look at this one. So first we will see the lower limit topology, and we need to find the closure of these intervals. Topology. Okay. So in this one, so first we will take, so given C belongs to 0 comma root 2, okay, any neighborhood of C must contain C comma D where D is greater than C. Okay. Now any neighborhood U. Now U intersect A at some point on C comma D, and therefore A is a limit point. I hope it is clear. Is it clear? So basically in the lower limit topology, the lower limit topology is by, wait a minute. So A comma B, this one. Yeah, so lower limit topology is generated by this basis, A less than B. So if you take any C belongs to 0 comma singleton, sorry, wait a minute, close 0 open 1 open root 2, okay, then any neighborhood U of C, how it looks like, it will be of this form, and it will contain C, close C and D, where D is any real number greater than C. It will be of this form only, because it has to contain C. Okay. Is it clear? It will contain of this form always, and this type of neighborhood will always intersect A at some point on C comma D. So sorry, C is always a limit point, therefore C is a limit point. Now if C is any point greater than or equals to 2, then the interval root 2 comma, okay, sorry, so C is greater than, so C, we can start with C comma D again is a neighborhood of C that does not intersect does not intersect E. Okay, so a similar argument, similarly you can show C less than 0 is not a limit point. Okay, so means A is 0 comma root 2, so A closer is nothing but 0 comma root 2, and so the A closer will be 0 comma root 2. Okay, fine. Now if we talk about B closer, similarly you can find B closer as B union close under root 2 and 3, so this will be close under root 2 and 3. Okay, now the basis, this one, so now the basis C. Okay, so in this case any C belonging to 0 comma root 2 is so what is the, okay, yeah, is a limit point of A. Okay, let U be any neighborhood of C. Okay, if now if C is rational, U must contain alpha comma beta where alpha is basically C and beta is rational. Okay, and so beta is rational and beta is greater than C, obviously. Okay, so this is fine. U must contain alpha comma beta, so it will be it will always going to intersect this one. Okay, so now if C is irrational, U contains alpha comma beta, okay, where alpha comma beta are rational and alpha is less than C and beta is greater than C. Okay, so it follows that U intersects wait a minute. Yeah, obviously, if C is irrational, you can find a rational here and rational here in between. Like C is here, rational here, alpha comma beta. So this implies that U intersects A. Okay, at some point alpha comma beta. Now any C less than 0 any c less than 0 cannot be a limit point. Because alpha is rational and less than c, okay, then alpha comma c 0 is a neighborhood of c which does not intersect a. Similarly, any c greater than root 2 can't be a limit point of a. Therefore, a set of limit point is nothing but 2. So a closure is nothing but 0 comma under 2. But here is the thing. But for b, which is nothing but under root 2 comma 3, this is the one. b is under 2 comma 3, but for b the b closure is nothing but under root 2 comma 3. We will see this one. If u is a neighborhood of under root 2, then u must contain something like alpha comma beta for some alpha comma beta are rational and alpha is less than root 2 and beta is greater than root 2. Okay, so it follows that root 2 is a limit point. No problem in this one. Okay, now if you take 3, so take c equals to 3. Now consider the neighborhood of 3. Okay, so if you take u as 3 comma 4, okay, so now this 3 comma 4, see the thing is the only problem you are getting is here also we can take in this one under root 2 comma anything, but this is not a neighborhood because this basis is a comma b, where a comma b is rational. Okay, here under root 2 is not a rational, that's why here under root 2 is not creating a problem, but in the next one it is creating. Okay, so we can take u is this one is neighborhood of 3 but not intersect e, sorry, b. So I hope it is clear. Is it fine? Ohana? Okay, fine. So see the next thing. So this is the standard fact. Okay, so okay, yeah, first recall what is Hausdorff space. So I will just recall what is Hausdorff space. Just wait a minute. Okay, so a Hausdorff spaces. Okay, so a topological space X is called Hausdorff space if for each pair of points x1 comma x2 belongs to X, where x1 is not equals to x2 is distinct point, there exists neighborhoods u1 of x1 and u2 of x2 respectively, such that u1 intersection u2 is equals to 5. Okay. Okay. Now there is a result. So I will just mention these results which are important. First one is every finite point set in a Hausdorff space X is closed. Okay, this is one such result. Okay, so this is also known as the T1 axiom. What is T1 axiom? A topological space is said to satisfy T1 axiom. So if a topological space is said to space X is said to satisfy T1 axiom if every if every finite point sets are closed. Okay, so this is called the T1 axiom. Just let me see something. Yeah, fine. Now here is a remark. Now we have seen that every topological space is a finite point. Every Hausdorff topological space satisfies T1 axiom. But what about the converse? Okay, does there exist a topological space satisfying T1 axiom, but it is not housed of? So it is, the example is R with finite complement topology. Finite complement topology. This we'll see in the problems, next problem. R with finite complement topology uh, is not housed of but satisfies T1 axiom. Okay, this is one thing. Next thing what we are going to see is that okay, another thing is, another result is okay, so let X be a topological space satisfying T1 axiom. Okay, again let A be a subset of X, subset of X. Okay, then a point, then the point X is a limit point of A if and only if every neighborhood of X contains infinitely many points of A. If and only if every neighborhood of X contains infinitely many points of A. Okay, another result is, which is important, is this we will use when we need to show when a space is housed of or not. So if X is a housed of space, then okay, so first I need to mention something. Convergence of sequence. Convergence of sequence. Okay, so how do you define? So let Xn be a sequence in X. We say that Xn converges, I will write in the short form CGS, converges to the point X belonging to X if every if for every neighborhood, if for every neighborhood U of X there exists and not belongs to a natural number, there exists some natural numbers such that Xn belongs to U for all n greater than equals to n naught. So this is what we mean by convergence of a sequence. And this point x is called limit. X is called only the limit, not limit point, called the limit of xn. Okay. Now if now result says that if x is a Hausdorff space, then a sequence of points of x converges to at most one point of x. Means either it is not convergent, but if it is convergent, it is going to converge at one point. Okay. And so, okay, so limit of sequence, and I will often write xn converges to x like this. This will be the notation I will use. Fine. So now we will see the problems. So let X be a topological space. Which of the following is less are true? It is the solution. So first thing is X is Hausdorff if and only if the diagonal is closed in X cross X. Okay. So suppose, we will see the first thing. Suppose X is a Hausdorff space. X is a Hausdorff space. Given X belongs to X, okay. Since X is a Hausdorff space, so singleton X is going to be closed. Is closed in X, okay. So singleton closure is nothing but singleton X. Now accordingly for every y not equals to x, okay, there is some neighborhood of y in x that does not intersect singleton x, okay. Just wait a minute. So we are showing that X is Hausdorff if and only if diagonal is closed in X, okay. So fine. So okay. So let us take the diagonal is x comma x such that x belongs to x. This is what diagonal is. So claim is to show that it is closed. Claim is closure is nothing but this one, okay. So clearly each of these points x comma x, okay, belongs to omega closure. So sorry, this delta closure, isn't it? This is trivial since this contained in this one. Now let x comma y belongs to x cross okay, so x cross x where x is not equals to y, okay. For any we take x dash comma x dash, there is a either there is either neighborhood of y that does not intersect x dash if y is not equals to x dash, or a neighborhood of x that does not intersect x dash if x is not equals to x dash. Okay, so what does it mean? So we have taken any x comma y such that x is not equals to y belonging to this product space x cross x. Now for any point x dash comma x dash, okay, there is either a neighborhood of y that does not intersect with x dash if y is not equals to x dash. Okay. Again, or a neighborhood of x that does not intersect with x dash if x is not equals to x dash. Means in particular, you take the cross product of this one, you will get this one, we will get hence there is a neighborhood in x cross x that does not intersect this is quite simple, intersect this. So any x comma y, different x comma y doesn't belongs to y closure if x is not equals to y. So this gives that delta is equals to delta, and sorry, delta closure is nothing but delta. Okay, so which means that delta is closed in x cross x. Conversely, suppose delta is closed in x cross x. Okay, so delta closure is nothing but delta. Okay, so you take any x comma y belongs to x, x is not equals to y. Okay, so we can find that there neighborhood of x and a neighborhood of y that are disjoint. Means so in this case we have already seen there exists a neighborhood of, so for any y we can take, so for this one, so for any y there exists a neighborhood of of y that does not intersect any x which is not equals to y. Okay, this is what we have seen earlier. So there exists a neighborhood of y that does not intersect with any of y. So again same thing for x also, means there exists a neighborhood of x and a neighborhood of y that are disjoint. Okay, so from where it is coming? For any y there exists a neighborhood of y that does not intersect any of x, because if it intersects, here we are using the closeness of this one, since this is closure is this one. If it intersects, that will belong to the closure x not equals to y, that will belong to the, but it doesn't have any sorry, x comma y, where x is not equals to y, will belong to the closure, which will be contradiction. Okay, so therefore x is a Hausdorff space. This space, okay. Now the next thing is okay. Next thing is we have to see that which of the topology is Hausdorff. Okay. So okay. So second thing first we have to see. Okay, so second one is it is related to the suppose x comma t is Hausdorff. If tau dash is finer than tau, then tau dash is Hausdorff. So let suppose x comma tau is Hausdorff and tau dash is finer than tau. Okay, so for any distinct points x and y, there are neighborhoods a of x and b of y in wait a minute, in tau that are disjoint. Obviously this is what we mean by Hausdorff. Now since this tau is contained in tau dash because this is finer, so this a and b both will be open in tau. So this therefore a and b are open in tau dash, and hence x comma tau dash is Hausdorff. Okay. Now you will see that R with the standard topology. This is the standard topology. So this is always going to be Hausdorff. Okay. How? So basically, given any x comma y belongs to R, we can assume that x is less than y. Okay. You take epsilon is equals to y minus x by 2. Okay. Then x minus epsilon comma x plus epsilon, okay, and y minus epsilon comma y plus epsilon. These are the disjoint neighborhoods. Intersection is phi basically, okay, and it contains x and y. So this is Hausdorff standard topology. Okay. Now the next thing we have to see is that tau 2. Tau 2 is what? Wait, just let me see. Tau 2 is this is on which page number? 10th. Tau 2 is finite complement topology. Okay, so the third one is R with tau 2. This is finite complement topology. Okay. So this is not Hausdorff. Why? Okay, just see this result. Okay, here we have some result which we have proved. Just let me see in the Hausdorff case. Yeah, so if X is Hausdorff space, then a sequence of point of X converges to at most one point of X. Okay. But in the finite complement topology, just let me see. Yeah. So you can see that in this one. In the finite complement topology, what we have, every basically sequence 1 by n converges to every point of R. Okay. So finite complement topology cannot be Hausdorff space, because if it is a Hausdorff space, we have that a sequence converges at most to one point, but here it converges to every point of R, so it is not a Hausdorff space. Hausdorff by result by result 3, result 3, 1 by n converges to 3, since 1 by n converges to every point of R. Okay. Fourth thing is K topology. Okay. So K topology is basically, topology is finer than Hausdorff. Finer than standard topology on R. Standard topology which is Hausdorff. Standard topology is Hausdorff. So the K topology is Hausdorff. Okay. Now, if we see the upper limit topology, so let x comma y belongs to R, x is not equals to y. Okay. So the intervals minus infinity to x and upper limit topology x to y are disjoint of x and x and y. Also note that this topology is finer than standard topology. Hence Hausdorff. Okay, this is fine. What is the next thing? So we have a okay, so let us do the technique. So this is fine, we have proved. This is true. This is Hausdorff. R with T2. T2 is finite complement topology. This is not Hausdorff. R with T3 is what? Okay, anyhow, whatever it is, you can check. This I will not do because order topology is not there. So now this is not true. Every T1 space is Hausdorff. So R with finite complement topology is T1 space, means satisfies the T1 axiom, but it is not Hausdorff. Again, product of two Hausdorff space is Hausdorff, and subspace of a Hausdorff is again housed of. This you can found in notes, lecture notes. Okay, so just let me see the other problems. Okay, just wait a minute. Okay, so I think we are done with the today's assignment. Okay, so you have any doubt, please let me know. Mohana? Okay, thank you. So we'll meet in the next session, live session. Thank you.